Okay, think about this. What if the biggest environmental headache wasn't, say, plastic bottles, but maybe the phone in your pocket? We're drowning in electronic waste.
But what if the solution wasn't just better recycling? What if it was, well, eating the electronics?
It sounds completely sci-fi, I know. But it's actually where some really cutting-edge science is heading. Think about it, our current gadgets, they're packed with stuff that just doesn't break down, chemicals that can be pretty nasty. And when these devices die, they become e-waste. That's a huge problem for the environment and, frankly, public health, especially in places that don't have great ways to deal with it.
Exactly. So today we're doing a deep dive into something called edible electronics. We're not just talking about tech that falls apart. No, this is about making devices from materials so safe, well, food-like, that your body can actually dissolve them, digest them, and even use them as nutrients, fully metabolized.
It's genuinely transformative stuff. Our goal today is really to unpack this for you, give you that shortcut to understanding what's going on. We'll balance the high-tech details with some pretty surprising facts, make it relatable. We're mainly drawing on a big review paper about edible electronics. It's by Priyanka Kataria, Arun Kumar Gupta, and their team, published in Trends in Food Science and Technology. A really comprehensive look.
And we've also got some fascinating details from an MIT study. This one's about a specific ingestible sensor. The research involved Giovanni Traverso and the famous Robert Langer, plus folks from Solero Systems and West Virginia University. That appeared in the journal Device. So let's jump in. What makes this edible stuff so different from, say, just transient electronics we sometimes hear about?
Right, that's a really important place to start. The distinction is key. When we talk about edible electronics, we mean these tiny, often micro-encapsulated devices. And they're made from materials, could be inorganic, could be organic, that are fundamentally edible and nutritive.
Okay, edible and nutritive. And they have a job to do inside you.
Exactly. They're designed to perform some kind of diagnostic task, maybe monitoring something, or even a therapeutic function, usually within the GI tract, the digestive system.
And then what? After the mission's complete.
This is the crucial part. The device materials are meant to be dissolved, digested, and here's the key word, absorbed, metabolized by the body, basically turned into nutrients it can use.
So it's not just breaking down into tiny bits that pass through.
Precisely. If it just disintegrates into little non-toxic pieces that your body doesn't interact with chemically, that's more like transient electronics. Edible means the components themselves become part of your body's chemistry, even if just temporarily. They have to be truly safe and, well, biologically integrated.
Right, yeah, it's a huge difference. And what's really grabbing me is the sustainability angle. It's not just about less e-waste, is it? It sounds like it connects to other big problems, too.
Oh, absolutely. The sustainability potential is massive. It fits perfectly with ideas like the circular economy. And here's something that might surprise you, our first kind of wow fact, maybe. Edible electronics could actually help tackle food waste.
Hold on. You're saying building circuits could help solve the problem that we waste, what, like a third of all the food produced globally? How does that even work?
It sounds counterintuitive, right? But researchers like Radovanovich and their colleagues had this really ingenious idea. They looked at food waste, specifically things like peels from oranges, potatoes, apples, carrots, the stuff we usually throw out. These peels are full of useful polymers and compounds.
So they're literally turning garbage into gadgets.
Basically, yes. They take these peels, dry them out, grind them into a powder. Then they use natural binders, things like honey or starch, to stick it all together and form functional substrates, the base layers, for circuits.
Wow.
So it directly takes landfill-bound waste and turns it into a necessary part of green technology. It's reducing waste and creating sustainable electronics, a real win-win.
Okay, that's genuinely clever. So we understand the why, making these metabolizable circuits. Let's get into the how. The ingredients. Every circuit needs conductors, insulators, semiconductors. But I'm guessing the materials here aren't your standard copper and silicon?
Not at all. The big challenge is finding stuff that works well electronically, but is also completely safe to swallow. Biologically benign, as they say.
Right. Start with conductors. The wires. What carries the current?
Well, initially, researchers looked at metals the body already handles in tiny amounts. Things like gold, silver, iron, magnesium, zinc. Gold is interesting because it's physiologically inert in its usual form. It just passes through you. That's why it's approved as E175, for decorating fancy foods.
Wait, but if you shrink gold down for electronics to like micro or nano size, doesn't that change things? Could it build up in your gut?
That's exactly the concern. Macro gold is fine, but micro or nano-sized bits, yeah, there's a potential risk of accumulation. So safety testing is absolutely critical, and it pushes researchers to find alternatives.
Safer alternatives like it.
Like activated carbon, you might know it as activated charcoal, food additive E153. It's cheap, easy to get, and you can safely ingest much more of it than those metals. We're talking grams per day, not micrograms. And it works. It's being used in things like edible supercapacitors and biofuel cells already.
And then things get even more food-like. You mentioned ionic conductors.
Right. This is where salts come in electrolytes. Just like in a sports drink, those salts carry charge. There was this great kind of fun example from Hamilton and colleagues. They actually 3D printed conductors using Vegemite and Marmite, those salty breakfast spreads, onto slices of bread.
Seriously, circuits printed on toast using Marmite.
Yep. Harnessing the electrolytes we eat every day, it shows the principle really well.
That's brilliant. And what about more advanced carbon stuff? You mentioned laser-induced graphene, LIG.
Yeah, LAG is a technique developed by Chengyan and coworkers. You basically use a laser to write conductive graphene patterns directly onto organic materials. Things like wood, paper, coconut shells, even potato skins. It creates really good conductors with low resistance, and it works on these soft, biodegradable bases. Super useful.
Okay, conductors covered. What about the insulators, the structural bits, the protective layers?
These are often materials we already eat as food additives. Things like cellulose, that's E460 to E469, or shellac, which is a natural resin they use to coat candies. Gelatin, even caramelized sugar can work.
But you mentioned one material is key for controlling when things dissolve, silk fibroin.
Ah, yes, silk. It's incredibly versatile. Silk fibrin, derived from silkworm cocoons, can be processed in different ways. Depending on how crystalline you make it, you can control its dissolving time very precisely. It could dissolve in water in minutes, or if it's highly crystallized, it can stay intact for years.
So you can tailor it for specific parts of the digestive system or specific release times.
Exactly. It makes it ideal for creating custom substrates or protective coatings.
And finally, the really clever bit. The semiconductors, the components that make transistors work, control the flow, maybe emit light.
This is where it gets really interesting. A lot of edible semiconductors turn out to be natural pigments and dyes. Indigo carmine, for instance, that's the food coloring E132, has been used as an electrode material. But maybe the most mind-bending example, highlighted in the review, involves something called copper-2-phthalocyanine.
Copicing doesn't exactly roll off the tongue. Sounds very chemically.
Get this.
Yeah.
It's a blue pigment, and it's commonly found in whitening toothpaste.
In toothpaste? You're kidding.
Not kidding. And here's the kicker. The research suggests the tiny amount most people probably swallow accidentally each day, maybe 0.5 milligram to 1 milligram, is theoretically enough material to make over 10,000 edible transistors.
Wow. Okay, that's officially amazing. A common toothpaste ingredient is a viable semiconductor for edible tech.
Right. A readily available, non-toxic blue dye with useful electronic properties. Who knew?
So we've got these incredible edible building blocks. Now let's talk applications. Why go to all this trouble? What can these things actually do inside us?
The biggest driver is definitely healthcare, revolutionizing how we monitor health and diagnose problems. And for that, we can look at the work by Traverso, Langer, and their collaborators at MIT and Celero Systems with their ingestible sensor.
Right, the smart pill. About the size of a big vitamin, you said?
Yeah.
What's inside it?
It contains an accelerometer. That's a sensor that measures movement and acceleration from inside the gut. By carefully filtering out all the background noise of digestion, it can actually pick up the tiny movements associated with breathing and heartbeat. So it measures respiration rate and heart rate.
And they tested this in people.
They did. In a small study with 10 volunteers, the sensor worked remarkably well. It accurately measured vital signs. And importantly, in one person, it actually detected an episode of sleep apnea, a dangerous breathing interruption. And afterwards, the capsule just passed through the body harmlessly.
That's incredible. But I remember reading the potential goes beyond just monitoring. They have a vision for intervention, right? Particularly for something like opioid overdoses.
Yes, that's a really powerful potential application. Opioid overdoses tragically often cause breathing to slow down and stop respiratory depression. So the researchers are working on integrating a dose of an overdose reversal drug like nalmefene into the same capsule as the sensor.
So the pill could detect the problem and deliver the treatment.
That's the idea. If the accelerometer senses that breathing has dropped below a critical danger level, It could trigger the release of the nalmefene right then and there, potentially automatically inside the person's home, maybe saving their life well before paramedics could even arrive. It's truly precision medicine in action.
Well, it really changes the game from reactive treatment to, well, almost preemptive intervention happening inside the body.
And speaking of precision, these edible electronics are also great for targeted drug delivery in general. You can use special coatings, and enteric coatings, for example, that only dissolve at certain pH levels. That means the device can release its medication specifically in the part of the intestine where it will be most effective.
Okay, so huge potential inside the body. What about outside? You mentioned applications in food safety.
Right, moving out of the body and into the supply chain. Edible sensors can be built right into food packaging. Think of them as smart tags. They could monitor things like temperature history, pH changes, even detect the gases produced by microbes as food starts to spoil, giving you a real-time picture of quality and safety.
Can you give us an example?
Sure. There was some work by May and colleagues back in 2020. They created a pH-sensitive film using sago starch, totally edible, and anthocyanins, which are natural pigments from torch ginger. This film literally changes color. It goes from pink to green if the pH level rises, which is a common sign of spoilage in things like meat or fish.
So instead of just a best before date, you'd have a visual indicator on the package telling you if it's actually still fresh, built from edible stuff.
Exactly. Real-time visual feedback. Much smarter than a simple date stamp. Now, all this sounds amazing, and the potential is definitely there. But we need to be realistic, too. There are some significant hurdles before we're all swallowing our sensors.
I can imagine. Just because the ingredients are technically food, I bet getting regulatory approval is complicated. What's the issue with bodies like the FDA?
It's a bit of a paradox, really. The function of the device often matters more to regulators than its composition. Because these things are intended to diagnose or treat conditions inside the body, they often get classified as medical devices. And usually, semi-invasive ones, putting them in the higher risk categories, class 2 or even class 3.
So even if it's made of sugar and starch, if it's acting like a medical tool, it faces the toughest approval processes.
That's generally how it works. The fact that it's edible doesn't give it a free pass as just food. We saw this with the first FDA-approved ingestible sensor system, Abilify MyCite. It used standard silicon chips, definitely not edible, but it set a precedent for the intense scrutiny these internal devices face, edible or not.
Okay, regulations are tough. What about the tech itself? Are these edible materials actually as good as traditional electronics?
Yeah.
Performance-wise?
Well, frankly, no, not yet, anyway. Edible materials generally aren't as robust or electrically efficient as conventional ones, like silicon. Performance is usually lower. Stability can be an issue. They're softer, more affected by the body's environment. Getting good insulation, managing electrical leakage with these materials is tricky.
Which probably means they need more power or struggle with battery life.
Exactly. You often need lower operating voltages to make things work, which puts a strain on the edible batteries, which themselves are limited by how much safe chemical energy you can pack into a tiny, swallowable space.
So lots of optimization needed there. And just making these things, fabricating tiny, precise circuits with, sticky, soft, food-based materials must be hard.
Oh, fabrication is a huge challenge, especially for scaling up production cost-effectively. But techniques like inkjet printing and 3D printing look really promising. They allow for very precise placement of these soft, often liquid-based inks at room temperature. You can't really bake these circuits like you do with silicon. The food ingredients would just decompose. So these gentler additive manufacturing methods are likely key.
And looking ahead, thinking about that sustainability goal again, what's the main focus for future research?
It has to be the whole life cycle. Yes, improve the performance and stability of the edible components. Definitely expand the library of safe, useful materials. But crucially, the manufacturing itself needs to be green. Using non-toxic processes, avoiding harsh solvents. The end product needs to be edible, sure, but how you make it has to be sustainable too.
This has been absolutely fascinating. A real glimpse into a potential future. Yeah. Let's try and boil this down. What are the top, say, 3 key takeaways for everyone listening?
Okay, first, edible electronics aren't just dissolving gadgets. They're revolutionary devices built from really surprising stuff. Food waste, gold, even pigments from toothpaste or vegetables designed to be safely used by the body metabolized like nutrients.
Second takeaway, the potential impact is huge. Transforming healthcare with things like real-time internal monitoring, super-targeted drug delivery, maybe even automatic overdose prevention, and also making our food safer and reducing waste with smart packaging.
And third, despite the amazing science, big challenges remain. The regulatory path is complex because they're treated as high-risk medical devices, regardless of ingredients. And technologically, there's still work needed to boost performance and efficiency using only safe, sustainable, edible materials. It's a vital step, though, towards tech that doesn't pollute.
It really does feel like the lines are blurring, doesn't it? Between food, medicine, technology. It's all starting to merge.
It makes you think, doesn't it? If our technology eventually becomes just, digestible ingredients, truly sustainable, will future generations look back at our era of toxic waste and just wonder, why? Why did we ever accept technology that poisoned the planet instead of potentially nourishing us?
A really powerful thought to leave us with. Thank you so much for walking us through this incredible field, and thank you all for joining us for this deep dive. We hope you found it as eye-opening as we did.